We've spoken about how the success of Moore's Law, the success of scaling, the incredible scalability of lithography has allowed us to make these smaller and smaller transistors, these more and more complex integrated circuits. But that's taking us over the precipice well into the nano world, where we've also said the rules are changing. And so in this lecture, I'd like to speak about what happens, how the rules of the nano world become manifest, and both how we can manage them. It's kind of one approach, how we can try to continue to scale, and there's lots of success in continuing to scale, by managing these effects at the nanoscale. And then the other approach, which we can pursue in parallel, and which does get pursued in parallel by researchers around the world, is to try to see what exciting new phenomena are available to us. What's new in our toolkit? What kinds of new classes of electronic devices can we make once we gain dexterity on the scale of a nanometer? So let me start with this first topic of, why is it a challenge? How does the world change when we get down to the nanoscale, specifically in electronics? And to do that, I need to take just a bit of time to describe in a little more detail how one of these semiconductor transistors works. This picture is showing a transistor in a cross-section. And laterally disposed are two electrodes through which current can flow. This is called the channel, and it's exactly as it sounds, just like water would flow through a channel. Here are electrons. Current is flowing through a channel. Now, on top is the control. It's referred to as the gate, and this gate is used to open and close the channel. But the specific mechanism by which it opens and closes the channel is as follows. Through the application of a voltage on the gate, we either attract a sea of electrons into the channel, enabling flow. We fill it up with water, our channel. Or, if we put on a bias, an electrical potential of the opposite polarity, we repel electrons away. Our channel becomes depleted. Current flow is no longer possible. Now you'll see in this image that the gate electrode is separated from the channel. It's distinct. This is referred to as the gate oxide. And this is one of the things that we love about silicon, is one of the things we love about transistors. This oxide is an excellent insulator. It prevents current from flowing from the gate into the channel. That's a good thing. Our control now requires us to expend very, very little current. Essentially, no current flows from the gate into that channel. But through the application of this potential, we modulate the flow. We fill or empty our channel, but it doesn't cost us any electrons. It just costs us the application of quite a small voltage. Now, the other thing that just makes us love silicon so much is that this oxide is, in the case of silicon electronics, it's the native oxide, silicon dioxide. That's great for a couple of reasons. It means that the process by which we grow it is a very natural one. We simply introduce our silicon wafer into a furnace. We introduce the right temperature, the right ingredients in terms of water and oxygen, and we can grow an oxide, and we can grow it on the nanoscale. We can grow it to be a couple of nanometers thick. The other thing we love about it is that that oxide is just inherently disposed to passivate or terminate the states of the silicon that is sticking out of the substrate, sticking out of the wafer. And so we have a natural strategy using silicon's own native oxide for passivation, for termination of these sites chemically, and for the formation of an oxide of essentially whatever thickness we want to grow it to. We just take a bit longer, we just increase the temperature a bit in order to grow a more complete oxide. Now, here's where things start to get challenging. We spoke about scalability, and a component of our scalability was our ability to make many, many transistors on one integrated circuit. But in the course of scaling, we've also shrunken. We've shrunken the lateral dimensions of our transistors to fit more into the same region of an integrated circuit. In so doing, we're forced to scale vertically as well. We are required to make this gate oxide thinner and thinner. Why? This gate has to induce this channel. It can't be too far away from where the channel is located. It has to have that influence for a modest amount of voltage. To induce this very conductive channel, we need to be very close to the channel, and we have to get closer and closer as our transistors get smaller and smaller. So this is a scaling challenge now that we have. Well, what happens when we make this gate oxide a couple of nanometers thin? Well, now we have to think about electrons as waves. Now we have to think quantum mechanically. And if the electron is a wave, as is depicted in this image, then through a very, very thin oxide, thin on the scale of the electron's own wavelength, that wave can be both on the left and the right side of this barrier. It is simultaneously, through the probabilities of quantum mechanics, it can be on the gate electrode where we want it, or this electron has some probability of ending up in the channel. Now, the thing that we loved so much about this transistor model, in which essentially no current flowed into our channel, we got a huge leverage in our switching. It cost us almost no current to switch a very large current. Now that advantage is compromised through tunneling. So this is an example of where quantum mechanics, if we don't change our paradigm, if we don't change our approach, starts to imperil the advantages of silicon electronics. Now, material science and nanotechnology to the rescue here. They have been able to come to the rescue on this particularly important issue. On the left is a transmission electron micrograph of a standard silicon gate. The SiO2, that's the glass. That's the native oxide that's been grown. These TEMs, by the way, are pretty incredible. The structure that you're seeing in these images, these are individual atoms. So with our transmission electron microscope, we're able to image individual atoms. In fact, this is another illustration of our concept from earlier lectures on how small you can confine waves. We're able, using electrons, to see things as small as electrons, to see things on the scale of about a nanometer. There's no way you could take pictures of like this using visible wavelength photons, which are so much larger. Now, so this is showing a gate oxide that's a couple of nanometers thick. And it needs to get so thin again so that we can control, through the gate, we can control the formation of the channel beneath. We can't have our gate electrode be too remote from our channel in order to effectively control it. Now, on the right, you'll see what's called a high K solution. And the high K is referring to putting down a different material with different properties. Folks have discovered how to put down an insulator that resides between the gate and the silicon that can be thicker. You can get away with making it thicker, but it can still induce just as effectively this channel, this inversion region, inside the transistor. And so it's able more effectively to transfer the impetus of the gate. It's able to modulate the current flowing, even though it's thicker. And as a result of being thicker, we've postponed the onset of our tunneling problem. We are able to make this gate oxide thicker and still have the same strength of modulation, but we do so without the cost of having this large current. So these high K dielectrics, these new materials, are very exciting and are very attractive. Now, you recognize, though, what we've done is we've given up one of the things we absolutely love about working with the native oxide, silicon dioxide. We love the fact that we could simply grow it and that it could passivate everywhere across our silicon. We could grow it in such a way that it formed itself everywhere across the entire wafer at the same time. As long as there wasn't any dust or anything, there were no pinholes. A pinhole would be an opportunity for current to start tunneling through, so it would be very bad. Now, on the right-hand side of this image, somehow we've discovered how to put a new material onto silicon that's not the native oxide of silicon, and it has to have all of those good properties. Well, this is where there's been some very exciting advances recently in how to put very, very thin, nanometer thin films of different materials other than silicon on top of silicon. And the technique is called atomic layer deposition. It's incredibly clever. So the materials that constitute these new dielectrics, an example of it is hafnium oxide. And so it's a two-component material. Hafnium is one of the elements in it, and oxide is the other. And folks have figured out through this atomic layer deposition process how to put down exactly one first layer of the hafnium, which then is very prone to react with oxygen, and then to waft over it a little bit of water or another oxygen precursor, and react that first half layer to form a full layer of hafnium oxide, and then to start again. And so we are truly building up, layer by layer, at the atomic scale, these perfect materials. And in so doing, we're also able to interface them perfectly with the silicon beneath. And so when we bring in our hafnium, it sees this structure, it sees this texture of the silicon surface, and the hafnium atoms go where they go in response to this landscape of silicon atoms that are exposed. So this kind of control is what becomes necessary in order to manage these interfaces, because a silicon atom with its unpassivated, its unsatisfied electron sitting up is very unhappy. And we have to passivate each one of these atoms individually and extremely well. So this is a great example of where by scaling down, by getting to smaller and smaller length scales, we confronted straight on the rules of quantum mechanics, the fact that the ground is shifting beneath us, the fact that our foundations, our physical foundations, are starting to change, and where Moore's law cannot simply be extrapolated based on the existing material set. But through innovation, through the development of new tools, like the atomic layer deposition technique, we're able to give more runway. You can see that as we go to further and further generations, we're going to start running into more and more problems. But this is a great example of where, a while ago, people called for the end of Moore's law. People said that inevitably we'll have to run out. The question is when. But there were people predicting 20 years ago that it would run out within 10 years. And yet these extrapolations have been able to continue till now. They've managed to surprise people. The longevity of the continued, straightforward, direct, challenging but direct extrapolation of Moore's law has surprised a great number of people. In fact, it's interesting to note that when Gordon Moore made his observation in 1965, that from 1958 until 1965 there had been this doubling every year, he did make a bit of a prediction. And his prediction was that Moore's law could be sustained potentially for another decade, until 1975. Well, he's viewed as a very brilliant man for a number of reasons, but the fact that it was sustained for so much longer, and the challenges that folks had to overcome now at the atomic, at the nanometer length scale, are remarkable, and many, many people have been surprised by this longevity of Moore's law. There's another challenge that starts to exist in these transistors when we make them smaller and smaller and smaller. And this comes from the fact that current can now leak in what we call the off state. And so when we try to turn the channel off, as we make this transistor smaller and smaller and smaller, we can still get, in what's nominally the off state, we can get some flow of current through this very, very short channel. And one of the solutions has been to try to wrap, to no longer really think of this as just a planar device. It's not just flat anymore. But instead, to start to think about how we can wrap a gate electrode around the sides, around the edges of one of these devices. Now here, ALD, atomic layer deposition, is very much our friend, because if we're going to try to wrap things, we can't just have a process of depositing an oxide that's directional, that will only grow vertically. We need a wrapper. We need a nanoscale wrapper. And atomic layer deposition provides a technique where, because we're working with the chemical reactivity of surfaces, because the hafnium atoms will stick to the sides as well as the top, we have a technique that's very prone to creating a nice, compact, continuous, consistent wrapper all the way around the edges of one of these transistors. Now, there is another challenge that comes here, which is we thought we were doing planar lithography, right? We thought that we were just building kind of a two-dimensional circuit. We were kind of working in a flat landscape, and then we were just putting materials here and there and there. But to wrap a gate around the channel involves etching into the silicon. It involves digging down into a little trench. And when we do that, there's the possibility of making damage. We're no longer dealing with something that's just a sort of a straightforward flat structure. We're starting to build in 3 dimensions. We're starting to build almost skyscrapers. We're starting to build silicon structures that have aspect ratios that are tall. I mean, they're very, very small, but from an aspect ratio, from a kind of architectural standpoint, they're starting to get tall on us. And so this advent of three-dimensional devices, there's also three-dimensional circuits coming, but this advent of three-dimensional devices is something that people have been waiting for because they knew that it had to happen, but has been viewed as very challenging. And now this is starting to show its value. It's starting to show that it can be done, and it's starting to show that we are able to continue to extend Moore's law by using these techniques, these new material strategies, new materials deposition strategies, especially at the few nanometer length scale. But I'd like to go on, and I'd like to talk about how we can do more than just try to sort of extend the paradigm using essentially the same architectures of circuits, and that new nanomaterials can be our friends in trying to extend the run of Moore's law. And here, not extend it by a generation or two, but maybe extend it by many generations into the future. And let me talk about two very beautiful and fascinating materials that are seeing great progress and that are showing real promise for extending the run of Moore's law. So the first one of these is called the carbon nanotube. And you can see a picture of here. It's actually a rolled up piece of graphene. In fact, this was the basis for a Nobel Prize in the early 90s for the discovery that it was possible to make these long tubes of a single atomic layer of carbon forming this hexagonal lattice, and that these could be synthesized, so we could build them, and then they could also be purified. And their purification turns out to be incredibly important. And let me explain why. You can imagine a sheet of paper. Well, let's take an 8.5 by 11. You could roll up from the tall side. You could roll this way. Of course, you could roll along the height of the piece of paper, or you could go to any arbitrary angle and you could roll up in many directions. Well, now let's lay out a sheet of graphene with its hexagonal, its honeycomb structure. I could roll it anyway, but in fact, there's a few fewer options. If I'm going to connect a carbon atom at the end of my rolling with another carbon atom, then I'm limited to a large but finite set of operations. So there's many different species of carbon nanotubes that can exist. They can have different diameters. They can bond. They can terminate one another once you finish rolling in different fashions. Well, the fascinating thing about these carbon nanotubes is that depending on how you roll them up, exactly what angle you roll them up at, their properties are completely different. They can be, for example, one can be a semiconductor and another can be a metal. And that's incredibly powerful. Now we have a diverse material set that can serve many different functions. We're just starting from the same building block, this graphene sheet, and we can make it into any number of different things. So that's a great opportunity. And it's a fascinating property of these nanoscale materials. But when you think about electronics, I mean, I've been using words like control. I've been using words like 1 in a billion doesn't work, we're in trouble if a piece of dust lands. Well, the same logic will apply here then, right? If we're going to try to find a way to build a transistor using carbon nanotubes, and there's much progress in doing that, then we're going to have to find ways to make sure that all of our carbon nanotubes are behaving the same as one another. And so hence the need for great purity and great purification. And there's been some very neat work on both finding ways to make all carbon nanotubes the same, and then also very interesting ways of purifying them. I mean, the smartest way to try to purify these nanotubes is to try to purify them based on their properties. So to ask them, to find some kind of technique for querying each one and seeing whether it's got the right properties. And there was some beautiful results published a couple of years ago in which people actually used DNA which selectively would stick to these nanotubes differently, depending on the sequence of the DNA and depending on the roll-up of the carbon nanotube. And so they were able to use that specificity to do some sorting. But it does also imply that when you're talking about 1 in a billion kinds of perfection, that we may also have to think about a different architectural or conceptual paradigm for building computers going forward. That we may have to think of ways to build computers where not every building block is absolutely identical, where we don't have complete control. When we do that, we can start to utilize nanoparticles, nanomaterials, carbon nanotubes that are similar but maybe not absolutely identical. And then we need to figure out new ways of architecting integrated circuits and programming those integrated circuits in a way that embraces the variability that occurs at the nanoscale. Now, graphene itself, before you roll it up into a carbon nanotube, has actually been a more recent star of the show in nanotechnology. It was the discovery and the understanding and the properties of graphene was the subject of a very recent Nobel Prize in Physics. And graphene is this very beautiful material. It's got this energy landscape above it that's also very rich and that has surprising properties for the transport of electrons. Electrons behave in weird ways within this two-dimensional, within this planar structure, something that's only a single atom, a single atomic layer thick, where electrons can propagate as waves through this landscape. Now the challenge, of course, is if you have a sheet of something that's half a nanometer thick, how do you lay your blanket down on something? How do you integrate graphene with a circuit, like perhaps a silicon circuit? Well, there have been a number of advances just in recent years where people have understood how they could put down a single perfect layer of graphene onto a substrate, and thereby they could start to control it. And so the rapid propagation of electrons, the fact that electrons are even more perfectly delocalized in graphene, the fact that they just skim along at incredible velocities over this energy landscape, this is something that people are now exploiting more and more, and that many people are very excited could be the basis for really a considerable extension in Moore's law. You know, one of the other ways of looking at the challenges inherent in extending Moore's law and in building integrated circuits that consistently work well and continue to scale, one of the ways of looking at the problem is that it's actually a problem to do with temperature. The reason why, the reason why is the following: when you crowd all of these little transistors together into smaller and smaller areas, scaling seeks to reduce the power each one utilizes, but nevertheless, the power density, the intensity of generation of heat locally on this integrated circuit, it grows and it grows. And so we're always looking for ways to avoid these leakage currents that we talked about, to minimize the voltages that we need to apply. But there's also a real need for techniques that allow us to whisk away thermal energy with excellent thermal conductors of heat. And here graphene has shown great interest and great promise as well. Now there's some very exciting work on using graphene to connect vertically down to the substrate to whisk away the heat laterally within the substrate. Graphene, it turns out, also has these extremely good thermal conduction properties. And so that quality of graphene, not for electron transport, but for heat transport, is starting to be exploited as well. I'd like to finish this lecture with talking about approaches that aren't direct extrapolations of Moore's law or ambitious and challenging longer-run extensions of Moore's law, but where instead we say, this nano world, this quantum world, it's weird. Surely it affords us properties, behaviors that we have not used in digital computing until now. Surely there are new ways, revolutionary ways of architecting our computers that can take advantage of this new facility that is offered to us from the nanometer length scale. And so here in this image I present an example of what's called a resonant tunneling diode. And here we're actually going to take advantage of a current flow in the vertical direction. We're going to leverage the flow of electrons from a top layer through to a bottom layer. We're actually going to use the same tunneling phenomenon that was the bane of our existence in extending Moore's law downward to thinner and thinner gate dielectrics, but we're going to use this tunneling to our advantage to make a new class of devices. Let's take a look at how it works. So you can see in this image now a representation with, on the horizontal axis, space in angstroms. 1 angstrom is 10 nanometers. and on the vertical axis is energy. And what this is showing is a calculated solution, a model-based prediction for how electron waves are distributed on the left and on the right. Now, the resonant tunneling diode is ingenious. What it does is that it recognizes that we can set up an electron in a particular state on the left of a barrier, and we can create a state, really an opportunity for that electron to go to on the right-hand side, and that we can ensure that there is strong coupling between the left and the right only if the electron takes on that particular energy, the resonant tunneling energy. And so what we do in a resonant tunneling diode is we apply a voltage. Applying a voltage is just giving an electron a bit of energy, so we can raise it up in energy. But until it sees this resonant transmission, this tunneling phenomenon, it's not going to go over to the right with any reasonable probability. And so we raise our voltage a bit, and essentially no current flows. We raise it a little bit more, and all of a sudden, we become aligned with this resonant state, and huge current tunnels over to the far side of our transistor. Now here's the thing that happens next that is not done within contemporary electronics. We raise the voltage even more, and we become off resonance. We lose the capacity to tunnel resonantly. Our current goes down again. This kind of behavior, instead of looking like what we call a monotonic characteristic, where for more voltage the current just keeps going up, but this kind of behavior where it goes up and then it goes down again, this is a shape of a curve, a shape of what we call a transfer curve that is not currently exploited in electronics. And yet what you can do with that is you can create multiple level logic, it's called. You can have many bumps that you engineer through many transfer states, and you can have stable regions within them. And so you can have potentials in currents that aren't just zeros and ones, but you can have zeros and ones and twos and threes. And so in principle, if we can figure out a good way to do computation based on this, we can embed more information inside every transistor. Instead of being limited to binary logic only, zeros and ones, two options, we can give ourselves many more options within every transistor. And so now, our scaling paradigm, instead of being fixed at one pair of states, a binary option 0 or 1 per transistor, we can scale not purely by just making that entity smaller, but we can scale by enriching the amount of information that can be conveyed or can be stored or can be processed within every building block. Now that in turn hands over from this exciting concept, that hands over to the computer designers, how do you make an integrated circuit on this? And there's certainly progress and there's certainly work, but it remains the case that today the integrated circuits that are used in your computer continue to rely on binary logic. In today's lecture, we started from the perspective that electronics is, and its evolution over time, is really one way to get at the nano world. That initially in the 1950s and 60s, there's opportunity to integrate more and more transistors in this very scalable way onto a single material, to do it monolithically. That this then drove the emergence of aggressive scaling and the emergence of Moore's law. And we scaled down and down and down. And we developed technologies, techniques, methods of fabrication, cleaner clean rooms, to allow us to build things smaller and smaller. And then inevitably we got to the nanoscale. And that is challenging and that is exciting. It's challenging because the rules do change on us. We can't avoid it anymore. As we scale more and more, we start to see these phenomena emerging. And nanotechnology and nanomaterials help us manage those challenges and continue to drive forth within this paradigm. However, no matter how far we go, there will be limits. And this field of electronics and of computing is looking for the next breakthrough. And it's looking to nanotechnology, to the new types of behavior that occur, not just as the problem, as in the first part of today's lecture, but also as the solution that allows us to embrace the behavior at the nanoscale and leverage it towards new paradigms in computation.